Welcome to the BrewSLM Academy. This is Track 0, Foundations, 9 short lessons that build the mental model you need before you ever touch a training script. We start at the very beginning, what a model even is, and end knowing how a language model works and where fine-tuning fits among the alternatives. No code in this track, just the mechanics defined as we go. Here is the path. First, what actually is a model? Strip away the mystique, and a model is just a function with knobs. You give it an input, it produces an output, and its behavior is set by a long list of numbers called parameters. Nobody sets those knobs by hand. They come from training. The model guesses, we measure how wrong it was, and we nudge every knob a little in the direction that reduces the error. Once training is done, using the model is called inference. The knobs are frozen, you feed in new input, and it computes an answer. And for a language model, that answer is just numbers turned back into language, one token at a time. So where do the knobs come from? Learning. First, we turn the word wrong into a single number, the loss, measuring how far the guess is from the truth. Picture that loss as a landscape stretched over all the parameters. Every setting of the knobs has a height, and we want the lowest valley. Gradient descent is how we get there. We feel which way is downhill and take a small step that way again and again. The size of that step is the learning rate. Too big and you overshoot, too small and you crawl. In practice, we work in mini-batches, and one full pass over the data is an epic. Repeat until the loss stops falling. What is the function we are training? A neural network. The basic piece is a neuron. It takes some numbers, multiplies each by a weight, adds them up, and passes the result through a nonlinearity. That nonlinearity is the entire point. Without it, stacking layers would collapse back into a single straight line, and the network could only learn straight-line relationships. Stack neurons into layers and layers into a network, and you can approximate astonishingly complex functions. It learns by backpropagation. Run the error backwards through the layers to find each weight's share of the blame, then let gradient descent nudge it. That same machinery, scaled up, is what powers language. A network eats numbers, but language is text, so we bridge the gap in 3 steps. First, tokenization chops the text into tokens. Common words stay whole, rarer ones split into pieces. Second, each token maps to an integer ID from a fixed vocabulary. Third, each ID becomes an embedding, a learned vector, so that tokens with similar meaning end up with similar vectors. There are also special tokens that mark boundaries, and a context window that caps how many tokens the model can see at once. Now the text is a grid of numbers the network can work on. How does the model relate tokens to each other? Attention. The problem it solves, the meaning of a word depends on the words around it. Self-attention lets every token look at every other token and pull in what is relevant in 3 moves: a query, a key, and a value. Many attention heads run in parallel, each looking for a different kind of relationship. Wrap attention together with a small feed-forward network, and you get a transformer block. Stack those blocks, and you have the architecture behind essentially every modern language model. One detail matters for generation. Causal masking stops a token from peeking at the future, so the model only ever uses what came before. Put it together, what does a language model actually do? It predicts the next token. The final layer turns the model's internal state into a probability for every token in the vocabulary, a guess about what comes next. It learned this from a simple objective: read enormous amounts of text and, at every position, predict the following token. Generation is just doing that again and again. Predict a token, append it, feed it back, repeat. Decoding is how we pick from those probabilities. Take the most likely, or sample for variety. And this is exactly what fine-tuning adjusts. The same next token machine, retrained to predict the tokens you want. Before you fine-tune anything, know your options. There are 4 levers. Lever 1 is prompting. Change the input, no training at all. Lever 2 is RAG. Retrieve relevant documents and hand them to the model at inference, so it has the facts in front of it. Lever 3 is fine-tuning, or SFT, where you actually change the parameters by training on examples. That is what this academy is about. Lever 4 is continued pretraining, building broad base ability, the most expensive option. The decision guide is blunt. Need knowledge the model lacks. Reach for RAG. Need a behavior or a format. Fine-tune. Don't train when a prompt or a retrieval would do. So why small models? It comes down to one axis, parameter count. Scale costs real things, memory to hold the weights, latency on every call, and money at scale. A small language model trades some of that raw breadth for speed and cost. But here is the honest part, and it is the rule this academy lives by. Small models genuinely give some things up. They are weaker on broad world knowledge and open-ended reasoning. What they don't give up is the narrow case. On a well-defined task, a fine-tuned small model is often good enough, and sometimes better at a fraction of the cost. The skill is knowing what you need. Don't reach for a giant model to do a small job. Last in the foundations, the shape of a real project. It is a loop. Data, train, evaluate, decide, then around again. Your North Star through every turn of that loop is the gold set. A small, hand-checked set of examples you never train on, the source of truth for whether you are actually getting better. Each stage has a good that looks different. Clean data, a run that converges, an evaluation that beats the baseline. And the rest of the academy maps straight onto this loop. The SFT and hands-on tracks teach the train step, the BrewSLM track wraps the whole loop, and the advanced track sharpens it. Two flavors of the same model family, base and instruct. A base model is what comes out of pretraining, a next token continuer over raw text. It knows a lot, but it is not a chatbot. The instruct version starts from that base and goes through extra alignment training, supervised fine-tuning on instruction data, often plus preference tuning. That teaches it to follow instructions, respect roles, and stop when the answer is done. Same parameters retrained. So which do you fine-tune? Almost always the instruct. It already follows instructions, so your fine-tune only has to teach your task. Reach for base only when you are continuing pretraining, or when the shipped alignment fights what you need. There is no universal best small model. There are constraints, and the smallest model that meets your constraints is the right one to start with. 6 dimensions matter. License, can you legally ship what you train from it? Check before training, not at deploy. Tokenizer family. It is a contract with your dataset and a hard constraint for offline distillation. Instruct quality. How aligned is the starting point already? Context length. How long is your input plus output? Size and latency. Default small, step up only with a reason the eval makes for you. And community. Does anyone else fine-tune on this? For this whole academy, we use small LM2 135M instruct. Apache 2 license, Hugging Face tokenizer, decent baseline alignment, 2000 token context, fits a single consumer GPU, broad tooling support. The smallest model that meets the constraints. That is the foundation. You now know what a model is, how it learns, how text becomes numbers, how attention and the transformer work, how a language model predicts the next token, the 4 levers you can pull, the trade between large and small, the shape of a project, the difference between base and instruct models, and how to pick a base. Everything from here builds on these ideas. Next up is Track 1, SFT Fundamentals, where we go deep on supervised fine-tuning itself. See you there.